Do you like beer? Do you like physics? Then this is the experiment for you. Okay, so for today's experiment, we're going to investigate how the volume of the foam or head of the beer changes after having been poured. For this, we're going to need a timer, a measuring cylinder, and some beer, obviously. We will then record the volume of the foam every 30 seconds and then plot a graph of volume against time. Hopefully it will give us a nice exponential decay curve like the one shown here in the exam paper. In exam questions, we're often asked to use the data from a graph to verify this sort of relationship, as well as make comparisons against the half-life of a radioactive source or the charge across a discharging capacitor. So after we've plotted our graph, I will show you the kind of things that we might be asked and how you would approach those sorts of questions at both GCSE level, which is age 16 in the UK, and at A level, which is age 18 in the UK. Now, the first thing we'll need is a results table, so something like the table that you can see on the screen now. We'll measure the volume of the foam every 30 seconds for 3.5 minutes or 210 seconds, so you might want to pause the video briefly whilst you copy that down, and then we'll begin. Now, because the measuring cylinder has a constant cross-sectional area, we could also do this experiment by measuring the depth of the foam in, say, centimetres, but because the measuring cylinder reads off in millilitres, it's easier for us to plot the volume, I think. So each time we take a measurement, we're going to need to measure the volume at the top of the foam, and we're going to need to measure the volume at the bottom of the foam, and then by subtracting one from the other, that will give us the total volume of the foam. Whilst it is quite relaxing watching the beer settle, I think that to save us all from 3.5 minutes of just sitting here, I'm going to fast forward through this section, so hopefully you'll be able to keep up with your measurements as we go. Good luck! Now we've completed our experiment and we've got our results, we're going to need to plot these results on graph paper. The convention is that the independent variable goes on the x-axis, which in this case would be the time, and then the dependent variable, which is the one we measure, would go on the y-axis, so that would be the volume of head. Right, so here's my graph and line of best fit. Hopefully yours looks somewhat similar. Remember that your line of best fit doesn't have to go through every single plotted point, it should just be one smooth curve. A very common mistake that students make is they force the line to go through every single one of the points. I'll talk you through some example questions on the sorts of things that you might be asked about this in an exam. Now, this sort of relationship is called an exponential decay function, which is a mathematical relationship where a quantity decreases by a consistent percentage over regular intervals rather than by a fixed amount. Now at GCSE you would only see this sort of graph referred to in questions relating to radioactive decay, but at A level they would also draw comparisons against a discharging capacitor, which also follows this sort of relationship. Okay, the first question we're going to look at is a GCSE level question, so let's read through it together. Use the graph to find the time taken for the volume of the head to halve, or find the half-life of the beer. So what we're going to need to do is pick an initial volume. I would say anywhere on the left-hand side of the graph is fine. You could use 385, which is where the graph started at time 0. I've picked 300 millilitres, and that corresponds to an initial time of 15 seconds. Then what we need to do is halve that amount, so we need to find the time it took for it to go from 300 millilitres to 150 millilitres. So then we read off the graph the time taken for it to get to 150 millilitres, which I make as 56 seconds. And then once we've got that, all we need to do is find the time interval between them, which I make to be 41 seconds. So the half-life of the beer is 41 seconds. The next question is another GCSE level 1. You could potentially be asked this at A-level, but I think it would be on the easier end of an A-level question. So let's have a read through it together. Show that the graph has the same form as a graph of number of nuclei, or activity, versus time for a radioactive source. So what we're really being asked here is to show that the graph follows this exponential decay function form, where it decreases by a set percentage at regular intervals rather than by a fixed amount. So in order to do this, first, we'll need to find the half-life of the beer once, which we already did earlier. So I read off at 300 millilitres and 150 millilitres, and that gave me a half-life of 41 seconds. And then what we need to do is show that when we repeat this process on a different part of the graph, that we get the same half-life again. So we could just use two arbitrary positions again, like we did last time, but what I'm going to do for my second reading is I'll see how long it took to go from 150 millilitres volume to 75. Reading off of the graph, that looks like it went from 56 seconds to 97 seconds, so that's 41 seconds again. And then if the graph is an exponential decay curve, then you'll find that the half-life is the same regardless of which part of the graph you read it from. Now, for the values I've picked, the half-life came out to be exactly the same, 41 seconds both times, but you might expect there to be a little bit of variation between the two numbers. If they were a little bit different, I think that as long as you justified your answer, you could argue it either way. So if you said the numbers are different, therefore it doesn't follow the same form as a graph of radioactive decay. Or if you said, oh, actually the numbers are so similar that I think it does follow the same form as a graph of radioactive decay, I think that either of those answers would be acceptable. Question 3 is definitely an A-level difficulty question. You can see that for this one I've zoomed in the graph a little bit to make it more difficult, which is a trick that they often do. Let's read through the question together. So, the graph has the same form as a graph of charge or voltage against time for a capacitor. A bartender initially pours the beer and considers the head to have fully settled once 3 time constants have passed. They can then serve the beer to the customer. Find the time taken for the head to have fully settled. The time constant represents the time taken for the independent variable to fall to 1 over E, Euler's number, which is 0.37 or 37% of its initial value. Now, the time constant for a capacitor is conceptually very similar to the half-life of a radioactive source, except whilst the half-life tells us the time taken for the independent variable to halve, the time constant gives us the time taken for the independent variable to fall to 0.37 of its initial value. In this question, you've been told that, and to be fair, even at A-level, you usually are told that the time constant corresponds to the time taken for it to fall to 0.37 of its initial value, but you could potentially be expected to work it out for yourself. And if you have a look at the maths that I'm just putting on the screen at the moment, then I've shown you how you can work it out using the information that you're given in your data booklet. The reason I've chosen 3 time constants for this question, and why it comes up quite a lot at A-level, is because electrical engineers often consider a capacitor to have been fully discharged after 3 time constants have passed, since at that point the charge will have dropped to 5% of its initial value, which corresponds to 0.37 of 0.37 of 0.37. If we could see more of the graph, then we could just read off the time interval taken for the volume of head to drop to 5% of its initial value, but with this zoomed in view we can't do that, so we're going to need to read off one time constant and then multiply it by 3. So our first step is going to be very similar to in the previous two questions. We need to read off an initial value. I've used 250 millilitres. It's going to need to be somewhere on the left-hand side of the graph. And then we just need to read off the time taken for it to fall to 0.37 of that value, which I reckon is 92 millilitres. So the time interval is from 27 seconds to 87 seconds, so one time constant corresponds to 60 seconds. Once we've found one time constant, we just need to multiply that by 3, so 3 time constants corresponds to 180 seconds, therefore the beer is considered to have been fully settled after 180 seconds or 3 minutes. For the fourth question, you can see I've zoomed the graph in even more, such that it almost looks like a straight line, but if you look carefully, you can see that the line is still slightly curved. So let's read through the question. A student suggests that the graph has the same form as a graph of number of nuclei versus time for a radioactive source, or charge against time for a capacitor. Using data from the graph, evaluate whether the student is correct. It is known that the initial depth of the head is 385 millilitres. If we could see more of the plot here, then we could solve this question the same way that we solved question 2, just by showing that the volume of head halves at regular intervals, but because we've got a much more zoomed in view here, we're going to have to use a more complex method in order to solve this one. Okay, so if you have a look at the 3 equations that I've just put on the screen, the first 2 will nearly always be in your A-level data booklet for you to refer to. The first one is for a capacitor, where Q is the charge at any given time, and then Q0 is the initial charge. The radioactive decay, N, is the number of undecayed nuclei remaining at any given time, whereas N0 is the initial number of undecayed nuclei. And then when we put it into the general form, K1 would be the initial value of the independent value, and then K2 corresponds to the decay rate, and in much the same way that a radioactive source with a larger decay constant will decay more rapidly, with the general form, a larger value of K2 will give a more rapid decay. Because we've already been told in the question that the initial depth of the head is 385 millilitres, we already know what K1 is. So you can see that I've put that into our example below. And then what I need to do is I need to rearrange this in order to make K2 the subject of our equation. We have to use a little bit of natural logs in order to do this. So hopefully you can follow the working that I've done here. I'm going to remove the working and just move the final result up the page so we've got a little bit more space to work with. Essentially, all we need to do now is pick 2 or more pairs of values off of the graph, put them into the equation that we've got and work out what K2 is, and if K2 is the same in each instance, then we've proved that it does follow this exponential decay form. I need to read one pair of values from the left-hand side of the graph and one from the right-hand side of the graph. So I'm going to start with 138 millilitres, which corresponds to 61.0 seconds. And when we put that into our equation, we come up with a value of 0.0168. And then for my second pair of values, I'm going to go for 113 millilitres, which corresponds to 72.6 seconds. And when we put it into our formula, we come up with a value for K2 of 0.0169. Our 2 values for K2 differ from each other by less than 1%, so in this case I think we're pretty safe saying that the relationship has been proven. As a rough rule of thumb, I would probably allow them to differ by up to about 5% before I said that the relationship was not proven. As before as well, I think that what the examiner really wants is to see that you've made a judgment call based on the numbers you have, so it doesn't really matter which way you argue it, as long as you back up your conclusion with data that you've obtained from the graph. Okay, last question. So we've still got the very zoomed in view that we had from the previous question. It's just that now we're looking at a different area on the graph. So we're actually starting at the beginning. So you see on the x-axis, we're starting at 0 seconds now. Let's have a read through the question. So a student suggests that the graph has the same form as a graph of number of nuclei versus time for a radioactive source, or charge against time for a capacitor. Using data from the graph, evaluate whether the student is correct. So the big difference between the previous question and this one is that we aren't told what the initial value of the volume of the head is, so that's just one extra step that we're going to need to insert here, and then we'll solve the rest of it exactly the same way as the last one. To find K1, which corresponds to the initial value for the volume of the head, we need to hop over to the graph and read off at time t equals 0 seconds that the initial volume was 385 millilitres. Now we've got K1, we just need to do much as we did for the previous question. We need to pick off two pairs of values, one from the left-hand side of the graph and one from the right-hand side of the graph. Work out K2 for each, and if the numbers come out to be the same, then we've shown that this is an exponential decay function analogous to a discharging capacitor or the radioactive decay of a source. My first pair of values are 369 millilitres and 2.5 seconds, which gives us a value for K2 of 0.0170. And then my second pair of values are 335 millilitres, which corresponds to 8.2 seconds. And when we calculate K2, this also gives us 0.0170. So we've got good agreement that the graph does follow this exponential decay form. I'd be very impressed if you'd managed to follow through all of these examples in real time without having to stop the video, so don't feel ashamed if you need to go back and pause the video and have a look through what I've done in greater detail. If you've got any questions or comments, then just get in touch below, and otherwise good luck with your exams.
Mad Panda.